Welcome to the video for problems 221 and 222 of Engineering 623. These problems are very similar. Both of them involve the Smith chart, but they don't require much writing on the Smith chart, and so it'll be possible for us to use just one Smith chart for both problems. And I'll go ahead and point out now, if you look at the Smith chart, we have one red dot over here at the extreme left edge of the Smith chart and a green dot over at the extreme right edge. And the red dot corresponds to problem 221 and the green dot to problem 222. So let's go ahead now for problem 221. This problem states, use the Smith chart to find the shortest lengths of a short-circuited 75 ohm line to give the following input impedances: A, Zn equals 0, B, Zn equals infinity, C, Zn equals J 75 ohms, D, Zn equals minus J 50 ohms, and finally E, Zn equals J 10 ohms. So in problem 221, since the line is short-circuited, the load impedance is 0, and therefore the normalized load impedance is 0 over 75, or 0. And so when we plot that normalized load impedance of 0 on the Smith chart, we get that red dot, as has already been mentioned, the red dot here at the extreme left edge of the Smith chart. So now for A, what is the shortest length so that we will have an input impedance of 0? Well, if we don't have any transmission line at all, we've already said the load impedance is 0, and so if there were no transmission line at all, then Zn would be equal to Zl, which is 0. So one way to achieve this would be to have a transmission line of 0 length. But if we don't count that, then we see that when we come up to the Smith chart, we start at the red dot and start moving in the clockwise direction so that we're moving toward the generator. The first time that we will come to an input impedance of 0 is when we've gone all the way around one time, and that is 1/2 of a wavelength. So besides the possibility of 0 length, the shortest is 0.5 lambda. On the other hand, if we were looking for an input impedance equal to infinity, we need to only go halfway around, actually over here to the location of this green dot. That corresponds to an input impedance of infinity, and so that's half a wavelength or a quarter wavelength, and that's what we get for B. Now for C, we want an input impedance of J 75 ohms. So the normalized input impedance then is J 75 divided by 75, or J times 1. So if we look here, J1 corresponds to right here at the very top of the Smith chart, and so to go from here to the very top is 1/4 of half of a wavelength, or 0.125 wavelengths. And that's what we have for C. D says we want an input impedance of minus J 50. So if the input impedance is minus J 50, Then the normalized input impedance is minus J 0.67. And if you look on the Smith chart, that minus J 0.67 is about right here. Is the numbers below are the minus, and here's minus 0.7, here's minus 0.6, so minus 0.67 would be about right here, which is about 0.406 lambda. And finally, to get to J10 ohms, if the input impedance is J10, then the normalized input impedance would be J10 divided by 50, or let's see, it was 75. The characteristic impedance is not 50 ohms, it's 75 ohms. So if we wanted an input impedance of J10, the normalized input impedance would be J10 divided by 75, which is J 0.13. And if you look at that here, 0.13, here is 0.1, here is 0.2, so 0.13 be right here, which is 0.02 wavelengths in the moving toward the generator. So 0.02 wavelengths. And that's the problem 221. It's just as simple as that. And now problem 222 is extremely similar. We want to answer all of the same questions, but for a line that is open-circuited rather than short-circuited. Well, if it's open-circuited, then that means that the load impedance and the normalized load impedance are both infinity. And so when we plot that, we get the green dot over here at the right edge of the Smith chart. And then as we go through, we still want to go to the same places as before. So for instance, for Zn equals 0, remember that is over on the left edge of the Smith chart. So to go from the right edge to the left edge is 0.25 lambda, as we see right here. The next question was for infinite input impedance, which we know is on the right edge. And so one possibility would be a transmission line of 0 length. Another one would be a transmission line of 0.5 lambda in length. And that's what we have here for B. And then for C is, again, we want an input impedance of J 75 ohms, which as before means that the normalized input impedance would be J1, which is at the very top of the Smith chart, J1 right up here at the top. And so to get to that point, you'd need to go 3/4 of the way around the Smith chart, and 3/4 of half of a wavelength is 0.375 wavelengths. And there we see that for C, 222. And then for D, we want an input impedance of minus J50, which means that the normalized input impedance is, as before, would be minus J 0.67. And we observed before that that was down about right here, and so which is at 0.406 lambda, and we start off at 0.25 lambda, so we go 0.156 lambda. So we can see here for part D. And then finally, the final question is we want an input impedance of J10, which means the normalized input impedance as before was J0.13. And so we want to come over here. Here's 0.1, 0.2, 0.13 would be right here at 0.02, about 0.021 wavelengths. And so we would go 0.25 plus 0.021 or 0.271 wavelengths. So two very quick and simple problems on the use of a Smith chart.